Okay, welcome back, everybody. Here it is Thursday on our fourth week of class. We only have one more chapter to finish, which we'll do on Monday, and then we'll start reviewing for the final, which is next Thursday. Okay, we have two more group activities to do. One is today, and then one will be on Tuesday or Wednesday of next week. I think it's going to be on Tuesday to make sure we have extra time to review things. And that activity, I'm not really sure about what I want to do for that. I think I want to just go through a series of things, but I'm still deciding what to do on that one. Okay, so the first thing we need to do today is we need to finish up chapter 15. We're going to talk about the enolate ions and how once we create that nucleophile, if we have a carbonyl compound somewhere else on the same compound, we have an opportunity for making rings and an opportunity for making ring rearrangements. So that's what we're going to work on today. And so that will be what we'll start with next. Again, my chat is open here. Go ahead and type hi or something in there, make sure it's working. And we have a total of 16 participants now. That's great. Okay, so, all right, great. The Zoom chat's working and everything. All right, so I've got my stylus out and I'm gonna start talking about rings and rearrangements, okay? So, remember that when we look at aldol condensations, that means you have a ketone or an aldehyde, and you're taking one of those alpha hydrogens or hydrogen next to the carbonyl, attached to a carbonyl, and that gives us an opportunity to create a nucleophile. Now, if we create let me get my red pen out here. If we create an anion here or here, okay, that deactivates our, this carbonyl toward attack, okay? So because we're forming that anion there, we will not have attack be on that site. However, if we form it in either one of these locations, it can come and attack either of whichever site we form it on, can attack that carbonyl. So the key here for what we're thinking about condensations is that you generate an anion, and that anion reacts with our carbonyls. And in all cases, that's what we're doing here. Sometimes we're reacting it with the same component we made the anion with, and those are what we call our aldol and our clasins. And then we have what we call our cross aldol and our cross clasin. In this case, this would be considered this particular compound would be considered a regular aldol condensation, even though we're doing it an intramolecular ring closure, okay? So let's talk about that a little bit more by figuring out how these rings can close. Okay, so if we look at that same compound there, the 2,7-octadione, notice there's two ketones, so it's a di, and then the one means it's a ketone. So we have octadione. We have a total of 8 carbons, so that makes it nice and easy to do. And then we have two possible positions that we can remove hydrogens. We have one here. There's 3 hydrogens on the end here. And then there's 2 hydrogens over here, okay? Now, there is some selectivity depending on your reagent on which one of these comes out. But for what we're gonna do is we're just gonna figure out if it's on one site, what happens, and if it's on the other site, what happens, okay? So the first thing we want to do is, now that we have a ketone species, we want to react it with a strong base like potassium hydroxide in this case. And when we do that, we generate an anion. We can generate it on that first alpha carbon or that third alpha carbon. Now I'm calling one of them the first alpha carbon because it's at the end of the chain, okay? But it is still the carbon that is next to that first carbonyl, okay? So if we were to number this chain, it'd be 1, 2, 3, 4, 5, 6, 7, and 8 over here. Okay, that's where the 3 and the 1 come from on our alphas. Okay, so let's take away a proton from this first alpha 1 carbon right here. And what we'll see is that if it because we have those sigma bonds and they are floppy, they can flop around, we can arrange it such that it forms this kind of intermediate where our anion is still attacking the back of our carbonyl, and we can generate a ring. And note there would be a negative charge here unless we've protonated it. And that creates a 7-membered ring, okay? So let's think about that. And then if we use a little more base on this, we would end up getting to our conjugated diene here, okay? Notice that forms, again, a 7-membered ring, okay? Now, we say that does not form, and the reason it does not form is that now that we have more than 6 members in our ring, that 7-membered ring is actually way too floppy. It has too many modes of freedom. And so we call this the entropy, or the disorder of the system, is too high. And so it doesn't form. But, so, and there's no other place for this anion to react. So if we formed the anion on the end here, we would only form this product here, okay? Now let's take it, instead of having that anion form on that alpha carbon, let's form that on the number 3 carbon. It's still an alpha carbon because it's next to the carbonyl. We're going to form that anion here, and notice that when we have that anion attack the carbonyl, it creates a 5-membered ring, which gives us an alcohol. And then, of course, by dehydrating, removing that water from that system, we get to our alkene, our conjugated double bond with our carbonyl. Okay, now, because we see this, we can take that proton again off either one of these alpha carbons right here. But when we do take it off the one here, it will not form this intermediate, and we do not get that. So what happens is it reverses back to our starting material if we deprotonate at that center, okay? So then if we deprotonate at the other one, it actually does form this nice ring, this nice 5 or 6-membered ring, which eventually will give us product here. So that means that, well, we can be forming this slightly, maybe, sorta, kinda. The fact that it is not favored by the energy in it, it'll go back to the original starting material, and then it will form this 5-membered ring. So let's look at that again, okay? And let's look at this compound here. Now, notice that the one before, that was an aldol condensation because we had an aldehyde or a ketone. Remember, the Claisen condensation is when we have an ester. And when we have an ester, that gives us an opportunity because we only have one alpha carbon for each of the esters. And so we know exactly which one it's going to remove, okay? The base is going to remove only this hydrogen here, giving us our anion only in this position. So let's go ahead and put our anion in that position here. And when we do that, this anion, because it can attack here because it's right next to that carbon, has to attack somewhere else. So we have to have it come and attack the only other carbonyl in our system, which is this one over here, okay? Now, notice when we do that, okay, we've now made our 5-membered ring, okay? So in this case here, our number 5 carbon is bonding to our number 1 carbon, so we just made this bond right here. Notice that, remember, the other half of this reaction, that ethanol goes away. It's removed from the solution because it's the better leaving group. It's removed from the compound as a better leaving group to close, to make our sigma bond here. And then those electrons came down to give us back our carbonyl. Okay, so do we see that in a Claisen intramolecular condensation, which is also called the Dieckmann condensation, we can make these 5- and 6-membered rings very easily, and it's easier to identify where the anion came from, okay? Let's go to another example here, okay? So we have this very complicated structure here, but let's take a look at it from our perspective of where can we form that anion, and how does that ring form, okay? So in this case here, where are we going to have our intramolecular interaction happen? Well, it can't, this is just the ester forming here, and this is an ester forming here. So this slide is in the wrong set of slides. I'm sorry, that's not what we want to talk about at all. All right. So let's actually look at the Michel addition. In the case of the Michel addition, we can also have an intramolecular Michel addition if we have all the three components required for the addition to happen. We have to have some kind of base, and we have to have our alkene in conjugation with our carbonyl here. Okay, remember, by having that carbonyl in conjugation with our double bond here, we end up having a resonance stability where we have a partially positive center here, our partially positive center here, and our partially negative center up here on the oxygen. Okay? So that means that in the case of this, we can actually get an addition at this part, and occasionally we'll actually get a reaction here. But most of the time we get this addition out here by our incoming nucleophile, our base, to generate our species, our Michel addition species. Okay, so what would it look like if we are actually trying to do this to do an intramolecular Michel? Well, we could do it something kind of a really interesting combination like this. For example, in this case here, we can add our amine to our Michel reagent. In this case, the Michel reagent is OET right here. And notice how that once we form there's two protons that can be deprotonated here. So the first one, Michel, adds to one equivalent of that. The second one came in from the other side and reacted with another amount of this reagent here. Now, once we formed that, there's a couple different things that can happen here. We can do it again, where we use another equivalent of this material to actually come in and deprotonate and react in these two sites. Or for the other reaction here, what we've actually done is we've deprotonated one of these. That one attacked this carbon here, giving us a way to have a dicarbonyl compound. And that ET just means ethyl CH2CH3. And then once we have this compound here, we can just go ahead and do our hydrolysis to give us our dicarboxylic acid. And then we have a beta keto acid, which means we can do that thermal decomposition of the decarbonylation, that thermal decarbonylation, because we have that to form our final product. Okay, so let's go ahead, and I want to draw a couple more intramolecular ones so we can see where they go, and so that we can get that down in our heads really well. I'm going to go back to my slides here, and there we go, that one right there. Okay, not that one there. Okay, I have enough room on one of these slides here. Let me just do it on this front side. Okay, so what I'm going to do is I'm going to do one more of these ring rearrangements with a different kind of compound here. Okay, so what we're going to do is we're going to just draw a random compound. Right here. Okay, let me not do that. Let me draw it as a methyl group right here. Okay, so we have this compound here, okay? Is that an O? Yes, it was. It was an OET, or it was an ester at the bottom, at the very bottom there. All right, so I want to show you one more thing about this, where we can look at this and see how it's going to form a ring. The first thing we have to decide is, where are we going to remove the proton? And we actually have 3 different choices, okay? So let me number these. This is number 1 because it's where the carboxylic acid is. So this is 2, 3, 4, 5, and 6, okay? Okay, so now we have 3 different carbons that are next to a carbonyl. So we have to decide where we're going to deprotonate and which one is going to be favored. So the first thing we have to do is say, okay, let's identify the 3 places we can remove them. We can remove them from, we can remove them from this carbon because it's next to the carbonyl. We can remove them from this carbon because it's next to the carbonyl, and we can remove them from this carbon. Okay. Let's decide which of these we're going to remove first, okay? This is the 2 carbon, this is the 4 carbon, 2, 3, 4, 5, 6, and this is the 6 carbon, okay? Now, look at how acidic these protons are. When we have an ester right here, that does not withdraw as much electron density as just the ketone because we have an electropositive atom here. What that means is that this, we're not going to deprotonate here. If we have to do something with a ketone or something with an ester, this one's actually more acidic because it doesn't have this electron donating atom here. So what I'm going to do is I'm going to say, okay, we're not going to remove that proton. We're only going to remove one of these 2 protons. Do we see why? Okay, these over here, these 2, trying to draw around them, these 2 are more acidic than the ones over here because the oxygen can donate a little bit of electrons to the system, making it less acidic. Okay, so we're not going to deprotonate over here. Okay, now we have a choice of, do we take the hydrogen off the 4 carbon or the 6 carbon? Okay, so the way we figure that out is, let's see what the intermediate would be if we did this. Okay, so I'm going to redraw this a little smaller up here. 1. Okay, so this is the way it would look straight here. But because we're trying to do an intramolecular interaction, because we know it's going to form on itself, let's rearrange this molecule so it's in a ring. Okay, I'm just going to try to draw it simply in the ring. I'm going to leave the ester at the top, right here, O. And then we have 1, we have 2, then we have 3, and then we have a carbonyl and another methyl group here. Okay, so if we just rearrange, this is the exact same compound, see? 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6, right here. Now we've rearranged it into a ring. Okay, remember we had 2 options for removing that proton. We could remove it from this carbon or this carbon. Okay, now look at this. If we removed it from this carbon right here, that's the only place that this anion we just formed can react. What size ring did that form? 1, 2, 3, 4. That would form a 4-membered ring, okay? So that is thermodynamically unstable because it's too small a ring. It's too, too small a ring. It's too tight. It just wanted to spring open immediately. So what I'm trying to get you to see here is that we're not going to remove the proton from this one. So that means we have to remove it from this one. Let's redraw it. such that we have a little more space here. What I'm going to do is I'm going to move this ester up here. O, methyl group here. So if we make our anion on this last carbon here instead, if we make our anion here, it's going to end up attacking here. What size ring are we making now? 1, 2, 3, 4, 5, 6. Okay, so we're going to make a 6-membered ring. Okay, so that's telling us where we are in our intermediate size. So that means when it reacts, it's going to do O minus O. I'm just showing the intermediate here. 1, 2, 3, and then a carbonyl here. And then this is the CH3 group here. And this is an anion. So that means what's going to happen is that this is going to kick in, and then this is going to kick out to giving us our final product, which is our 6-membered ring. And it turns out to be a beta diketo compound. So that's going to decompose to that. So we can take any structure and figure out exactly which ring side is going to be majorly formed by looking at that intermediate. If the intermediate can form a 5 or 6-membered ring, that is the ring it's going to form. All right, questions on that? Okay. All right, so that takes us to the end of our enolate ion chapter. I want to just review one thing about that. I want to review acidity of the different protons and the names of the reactions real quick so that we have it straight in our heads, okay? So whenever we have aldehydes and ketones, we call that an aldol condensation, okay? Whenever we have an ester, that's what we call our Claisen condensation, okay? If we have an aldehyde where one of the substrates does not have alpha hydrogens that it can pull off, but the other does, that means we get selectivity about where it reacts, and it's called a cross Claisen because one substrate, in this case, this one, has no alpha hydrogens. Therefore, you can only make the enolate with this, and if we only make the enolate with that, it'll only attack that. So that's what crossed means. It means you have two substrates and you selectively show which one's going to attack where. And that same thing happens in the Claisen condensation. Notice this one right here is two of the exact same materials. We're deprotonating here, and then it's attacking to the carbonyl to give us our substrate here. Yeah, let me redraw that. We make our anion here, and then it attacks the carbonyl there, giving us our product. Actually, that's not the way it happened. Sorry. We made our anion here, and then it attacked there, giving us our product right here. So that's the regular Claisen, but when we have an ester that doesn't have acidic protons here, we call that the cross Claisen. And that would look like this. Notice that we still have an ester, but here we have a phenyl ring. We could also have any other trisubstituted carbon. Anything that doesn't let us have this available to make an anion. And now this is the only place we can make our anion, and so it has to attack in that position, giving us our attachment, okay? So I like to use the cross Claisen to help me figure out exactly which substrate was which, because you always make the anion is the one that maintains the ester. The one that got attacked is the one that ends up becoming the ketone. Okay, so there we go. I got some lag going on there, but all right. So aldol, claisen, cross aldol, cross claisen, and the next one is the Michel. And you can recognize the Michel addition because of one of your substrates is a diketo species, and one of your substrates is a ketone or ester plus a double bond. So those are the ways to recognize each of these reactions, even though they undergo some of the same mechanistic points where they form an anion, the anion attacks something. In the case of the aldol and the claisen, we're attacking a carbonyl. In the case of the Michel, we're attacking a double bond next to the carbonyl. And it's all because of the resonance. All right. And then we also talked about the decarbonylation reaction, but we also talked about that in the carboxylic acids as well. All right, questions on that? Okay, I'm gonna stop sharing. Okay, so that's all I have to say about chapter 15. The homework lets you go through a lot of the identifiers of, oh, is it an aldehyde, is it a ketone, is it an ester, and that helps you do it. Now, the only other thing I want to make sure we look at is the idea of what things are more acidic and what makes them more acidic, and that's this here, where we want to kind of have it straight in our heads that when we have a hydrogen alpha to a carbonyl, we can remove that hydrogen right here. So in the case of the ester, right here, notice the ester is less acidic than the ketone here, and that has everything to do with the oxygen here, making it a little less acidic because that oxygen can donate electron density.
I don't see the screen that you're sharing.
Oh, sorry. Thank you. Oh, screen share. Okay. Can we see the screen now?
Yes.
Okay, great. All right. So if we look at this is our full table of acidities and things. I'm going to blow it up so we can look at just the bottom two. These are the least acidic substrates that we can generate enolate ions on, okay? And so the key here was that this is the first place we can do it, right here. And the least acidic of these protons here is the one that's next to an ester. So it's next to a single carbonyl, and it's next to the ester here, in this case, that's an ethyl group, so it's the OET right here. Because this oxygen has electrons on it, it decreases the acidity of these alpha protons. Okay. So the next thing up is just with one carbonyl but no oxygen, which gives our ketone, okay? That's our ketones or our aldehydes, both have acidities at this level, okay? So the least acidic proton we will ever remove for a claisen condensation is one of these esters. And then once we go to the aldols, we have the aldehydes and ketones, which are a little bit easier. Okay. But like I said before, we can actually make it even better for us by having two carbonyls. So that's the case of this right here. So we have an alpha hydrogen in between two carbonyls. In this case, it has two esters on it. So it's the least acidic of the dicarbonyl compounds. We take out one of those esters and it's a little more acidic. And then if we take out both of the esters, it's even more acidic, okay? So one carbonyl gets us enough acidity to do these reactions. Two carbonyls make it even better. And the ester is less acidic than the keto ester, which is less acidic than the diketo compound. Okay, so that's makes it kind of, I think in my head, this is telling me that I know exactly where the proton's going to be removed based on this level, this series of acidities increasing as you go further and further away from having an oxygen bound to a carbonyl. All right, any questions on that? I'm gonna stop sharing, bogging down a little bit. Okay, so that's all I have to say. Will we have self-test questions for chapter 14 and 15? The answer is no. Now that I have availability to have the homework be reviewable, we're not going to have those self-test questions, but you can review them, unfortunately, after you turn them in, which they're due on noon on Friday. In the future, I think I should have them due the day before, so you'll have them to review before the exam. So, but that's not in the syllabus this semester. Okay, sorry, I'm gonna mute my phone, my watch. Okay, any questions over chapters 13, 14, 15, or 12? So remember, we started with our aldehydes and ketones. All of these chapters are related to those carbonyls, how to make them, and how they react. Then we had the carboxylic acid derivatives, and a nice kind of, we're going to do an exercise on the different interderivatives related to that. Okay, let's see. Yes, you will be able to review homework after it's submitted. You should be, after the due date. You should be able to do it after the due date. I have a question in the, I have a question in the Zoom chat here. Will we have self-test questions for 14 and 15? And the answer is no. I did talk to Top Hat, and you will be able to review homework after it has been due, which means you will be able to review all homework for the final. You will be able to review all homework for the final because it's all due before at least a day before the final. However, it's not going to be due for our exam number 4. Okay. Okay, when doing the group activity, what do you recommend referencing for help? Well, I mean, the group activity is open book, open notes, and it's an opportunity to, share ideas and say, hey, what about this? What about this? What about this? And then come to a consensus about what the correct answer is. So one of the great things about doing the group thing is that you can have a weird idea and you'll say, well, what about this? And then people can say, well, let me see. And does it fit? Does it make sense? And then you guys can kind of work through it and come to an understanding. Okay. So we won't be able to see what we got wrong on homework 4. That is true. I'm sorry. I will be fixing that the next time I do this. This is the first time I've used this platform, and I was unaware that that was what was going to happen. Is it possible to take a practice exam or something for the final? I was going to have review sessions, and you have access to all of the homework before. So I think using those homework questions as a review would actually be a part of that. Can we review the patterns for the group activity? Which patterns? All, okay. Okay, yeah, so we'll look at, things to look for, like patterns of mechanisms. It's going to do one of 5 things. Look for patterns in clasins. It's always esters. Those kind of things. We'll be doing that. Okay. So as far as going through the homework, one of our activities is actually going to be the for the review is going to be going through all of our nomenclature rules and priorities. Now that we have them all in place and we know that carboxylic acids are the highest priority, let's go ahead and do a few examples where we rack and stack functional groups and actually solve those. That's going to be one of our activities for the review. The other one is going to be looking at what we call all of our reactions that we have and saying, oh, I can make an aldehyde into a carboxylic acid. How would I do that? I have 3 ways to do that. Oh, I have an alcohol. How would I turn it into a ketone? Okay, well, I have a ketone. How can I turn that into an alcohol? So we're going to go through that as another exercise, and that kind of helps to codify and identify all of our different reactions that we've looked at. Okay. So in general, the questions on the exam are going to be like the ones we have in class. I mean, on the previous exam and the homework. I'm going to try to ask you one-step questions. What is the product of this one reaction? What do we call this type of reaction? Which is the strongest base? Which is the best nucleophile? Things like that. I'm not gonna make you, do based on question 3, what's the answer for the next 5 things? I won't do that. And part of that's because if you got one wrong, you're gonna get them all wrong. So, okay. So we are out a little early. I'm really open for questions and stuff. What I'm going to do now is I'm going to stop recording since this is the last of the lecture.